Hi everyone, my name is Yu Xiaohang. I'm a blockchain security researcher at Chanting Technology. I'm currently leading a blockchain security group, and our daily work is to find zero days in various of blockchain projects, including blockchain systems, smart contracts, exchanges, and wallets, etc. Today, I'm going to share you with the idea of EVM Opcode JOP. JOP means jump-oriented programming. I'd love to invite you to interrupt me if you have any questions, but it seems like I can't receive your message in real time. So please contact me through Gmail or Twitter instead. My ID is present here. So let's talk about the background. What is it? What is this topic about? I'm gonna present you the blockchain challenge of the real world CTF 2018 finals named Opcode Monica. Before this challenge, most of the blockchain CTF challenges fall into two categories. One is combining some simple vulnerabilities like reentrancy or integral overflow. The other type is reverse engineering, but they simply just hide the source code, let the players to recover the original logic, then again exploit the same kind of basic vulnerabilities. So I want to try something new. So I took the idea of ROP and want to examine it in smart contracts. It turns out that we can use this idea, the drop, to create new type of smart contract honeypot with the help of runtime code replacement. And it also provides ideas for later blockchain CTF challenges. So I think it's a good starting case to start learning something about Ethereum smart contract reverse engineering. And this talk will hopefully follow this outline. I will walk you through the description and the solution step by step. So first, let's take a look at the challenge description. Opcode Monica is a brilliant girl. Anyone who solves her challenge could win some prize and her heart. About the challenge environment, it sets up a private chain for each player, which can be connected through a RPC interface. Then it highlights the target contract address and the player account, and it also provides a source code query interface. You can provide a contract address, and it returns with the corresponding source code. This is to mimic the verified source code function of Etherscan. The genesis file of the private chain and the private key of the player account is also provided to the players. With this information, the players can start the challenge now. And their goal is to drain the target contract, transfer all the Ether to the player account. Specifically, the player account balance should become a large number, and the target address balance should become 0. If these two conditions achieved, the admin account will send the flag inside a transaction, and the players can get the flag. Okay, the genesis.json is very simple. It allocates some initial balance to the player account and starts the private chain in PoA mode. This is to reduce the resource consumed by the game server. So basically, there's nothing for players to worry about. Then we come to the main game. So by querying the source code server with the targeted contract address, we can get the game contract code. The code includes two contracts, the Opcode Monica game, let's call it AM game, right? And a logger. And according to the server, the first contract is the main contract on the target address, which is the AM game contract. And the logger contract is used inside the game contract. And there are three public functions in the game contract: start, new round, and the answer is. Okay, let's take a look at them one by one. First, it defines three variables: questioner, question, and the answer hash. The start function basically takes in a pair of a question and the answer, record them in those three variables, meaning that the game is initialized. The new round function acts almost the same with the start function. It takes in a pair of question and answer and record them, meaning that the game is refreshed to a new round. Expect that only the questioner can start a new round, and this operation will be logged by calling the logger contract functions. The last function, the answer is, this can be called by a game player with an answer, right? If the answer provided by the game player has the same hash with the answer set by the questioner, then the game player wins this game, right? He or she will get all the money from the contract. Then he or she become the new questioner and can start a new round. Besides, please note that you need to transfer one ether to the game contract at the same time. Otherwise, it doesn't allow you to answer to participate in the game. So we kind of got a feel of the EVM game, right? And just mention it, the programming language we used here is Solidity. It's designed by Ethereum and is mainly used in smart contract. It has its own IDE called Remix, and it has an online version which is very convenient. So with the help of Remix IDE, players can easily interact with this game contract like this. The player only need to fill up the answer string over here, and click the answer is button. The IDE will send the transaction to the contract and take care of the rest of the things, right? By the way, players can also check the current question by clicking the question button. Okay, now after the description, we already got the basic idea of this game, right? Now let's play. Back to the contract. Now our situation is that we can know the value of answer hash by reading the blockchain storage, right? But obviously, we can't recover the plain text from the hash. Therefore, it's hard to win the game. But then, by checking the code, it's not hard to notice a fact that when the questioner starts the game, the answer was passed in as string type, which means the plain text is probably already exposed in the plain text in the plain transaction data. If so, we just need to find out the transaction and extract the answer directly from it, right? So we want to traverse all the transactions related to the game contract, trying to identify the very last call to start function or new round function. And luckily, there's only one call that calls directly to the game contract. It's sent from the challenge designer and is included in block number 23. Before check the input, here's a background knowledge. Usually, the first 4 bytes of the transaction input data will be further interpreted as function signature, which is used to declare which function it is calling to. And we can easily verify that this 4 bytes is exactly matches with the start function, right? Nice, this looks promising because it means the following data must be the string parameter, question, and answer. So if we interpret this hex data as ASCII characters, then we got the question string. In Madagascar, you cannot take a picture of a llama with green hair. Why? This question string matches with the question string we got from the Remix IDE, right? And note that the leading byte is the length, represents the length of the string. Then the last string must be the answer. You need a camera instead of gray hair. Great, we got the answer. Yeah, we got the answer to the question. Okay, let's try it. Put the question here and transfer 1 ether and send. But it turns out that it fails, and you lose 1 ether. So what's wrong here? Actually, it's a little tricky. If we iterate all the breaks, we'll find another transaction that seems not related to any address we know, but it's actually very important. And this transaction is sent from the challenge designer to none, which implies it's a contract creation. Note that the block number is 19, means it happened earlier than the previous transaction we were analyzing, right? Since it's a contract creation, so the new address can always be calculated, and with the new address we can query the challenge server and get the source code. It's a small contract and executes only one action during the creation period. It calls the start function of address t. By analyzing the input data, we know that the address parameter t is A9E6 blah blah blah, which is exact the game contract address, right? So we keep moving. The question string q is the same with what we know, right? And the answer r is just a single character r. Okay, recall that the start function only takes into effect by the first time. So since the last transaction we were analyzing is executed later than this transaction, it actually won't overwrite the result, right? Which means the real answer now is just this single r here. And this is the first and the easiest trap at design in this challenge. I'm hiding the actual function call in an internal transaction. Okay, since we got the real answer, let's try it again. Click send, but it failed again. Well, since I just said that was the first trap, so this is somehow predictable. But from the player's perspective, it's not that easy to accept, right? So what's wrong here? So what's wrong this time? Let's back to the function again. We've got the correct answer and send it with enough ether, so there should be no problem here. And the only suspicious thing is the logger, right? But there is nothing suspicious in the logger code. But is this the real code? Remember that this code is provided along with the game contract address, not necessarily consistent with the logger address, right? So to prove it, let's just query the code server with the logger address. And it's indeed running a different contract named logger agent, but after view it, seems like it doesn't break our logic. But let's see. Apparently, the calling log function doesn't exist in the logger agent contract. And according to this agent, if we made a function call which doesn't match any function in logger agent contract, it will hit the fallback function and delegate it to the actual logger contract, right? Besides, the agent owner can set the logger address at any time. In this way, the developer actually can make the logic upgradable. So it looks still good, but it's not that simple. If we do the calculation, we'll find that the signature of the function Opcode Monica wants to keep a log of the winner is 0x09005010, and it has the same signature with upgrade function. There's a function signature collision here. So when it calls Opcode Monica wants to keep a log of the winner, it won't call the fallback function. Rather, it will actually call upgrade function because they have the same function signature. Clear, right? And because the game contract isn't the owner of the agent, so it can never pass the only owner check of upgrade function. Thus, the function call will fail and get reverted, right? And it is this reason that causes our second trial failed. And yes, this is the second and the third trap I set up here. Is a honeypot combining fake code and function signature collision. When I was designing this part, I found this collision by brute forcing a common name database. And this is the reason why this challenge is called Awkward Monica, right? Okay, so now we figured out why our cars failed. It's kind of great, but it looks like this is the dead end. So where is the backdoor of the honeypot? If we want to if we want to solve this challenge, if we want to move on, we need another breakthrough point. Okay, that's enough for a warm up, and let's start to talk about reverse engineering. Let's back to the AM game again. By looking at the constructor, we noticed that these assembly snapes are suspicious, right? Very suspicious. To understand what do this Opcode do, we need to understand the general contract creation process first. So usually the data of the contract of a creation transaction consists of 4 parts. First is the creation code, which is relatively short, then followed by the contract runtime code, which is the actual contract code we are creating. Then there's a fixed length of metadata called swarm hash. And the rest of data will be interpreted as the constructor parameters. The creation code basically does 2 things. First, it executes whatever is written inside the constructor function. Then it copies the runtime code to a piece of memory and then returns it to the EVM and terminates the whole creation procedure. After this, the data returned by creation code will be stored to EVM and binded with the contract address. Then the whole process ends, right? Now we can analyze the transaction input data of our game contract. Okay. We can iterate through all the blocks to get this contract creation transaction data. To explain the following logic, let's temporarily switch to the game designer view, right? And as we said before, the first part is creation code, right? The second part is actually the parameter, which is the bias variable A in the constructor. So the runtime code and the swarm hash here, they are actually eliminated because I enabled the compiling optimization, and this is intended to keep it short. Now that the assembly code is inside the assembly code is inside the constructor function, it will be executed inside the first part, the creation code, right? Like we just said. So and it's right here, right? PC push E1 add and then jump. So what does this assembly code do? It adds up E1 with the program counter and jump to that new position, which basically hijacks the control flow, right? And force the program to jump to the beginning of the parameter A. Disassemble it. It basically does 2 things. First, store a value 262A to some position. Then return a piece of memory. So here's the plan. Explain. Usually, the return instruction is executed at the end of creation code. But now, since the control flow is hijacked, it hits return ahead of time in the parameter field, which means as the owner, I can control the creation code to return anything I need, right? So in this way, the runtime code does no longer match to the source code it compiled from. And the code being returned here is the rest of the following data. In other words, I've replaced the real runtime code with this little trick. And this is the reason why we failed earlier during the warm-up. As a designer, now we can do lots of malicious things like simply insert a backdoor to retrieve money at any time, or change the game logic, or make a complicated honeypot contract. Well, no worries. I'll demonstrate a possible way to utilize this type of honeypot. And back to the player's view. We want to figure out what does the malicious bytecode do, right? So the clumsy way is to decompile the whole binary. Well, we can do that, but let's try a smarter way. Let's compare this binary with the original binary compiled directly from the source code without interruption of the hijacking assembly code. And here is the compare result. So most of the bytes match with each other, right? But there are three differences. So the backdoor must be hidden in this different bytes, right? And let's check them one by one. The length of the first difference is 0x21, which is 33 bytes. And here is the different here's the different 33 bytes. So what is changed here? Remember that this is inside the answer is function, right? So the modified part is shown in the red boxes. And basically, it just changes the transfer sentence to a new gadget. And if the core data size equals 0x A0, it will jump to the trailing 4 bytes of the sender address. This means we have an arbitrary jump in this Ethereum contract. Okay, so the next question is, where do we want to jump to? Unlike a traditional architecture, jump in EVM can only land on a particular instruction, like 0x5b, named jump destination. And by searching through the whole bytecode, we found that there are 71 0x5b bytes. Well, it's not too much to brute force, but let's just put it here for now and move on to check another difference, right? So we just skip the second and ahead to the third difference. So the third difference is of 35 bytes long. And these are the very last bytes of the whole contract. We can notice that the prefixed bytecode has a special format here. And according to the Solidity official docs, this is the metadata segment. And the different 32 bytes are the value of swarm hash. And the change of this value does not affect the execution control flow. So this looks normal, right? But check here. Here is a 0x5b, a landing point, right? A jump dest, a landing point instruction, and after it there is a delegate core. So this become very suspicious and very likely that we need to jump to here and execute some malicious code by the delegate core, then jump to another place to end the whole execution, right? Okay, so now we have a plan. First, we need to call the answer is function and trigger the arbitrary jump. Second, we want to somehow jump to the delegate core to execute malicious code, but the delegate core consumes many parameters in the stack, so we need some other gadgets to prepare the stack, right? Looks good for now. Now let's check the last difference. It's only 1 byte. And it changes from 7F to 56. If we disassemble the original version, is a push instruction and pushes the following 32 bytes to the stack. By the way, the push the data comes from the sample answer string. So the very last 1 byte difference changed from push 32 to a jump instruction, and it's actually freed the following bytes from the data segment to executable instructions, right? And there's another jump destination. And let's see what's happening from this jump destination, okay? First, it pushes a value 0x20 to the stack, and then push another value 40 to E, and it's 2 bytes long, so push 2 is using here. Then put the caller address on the stack, and the ext code says instruction. This instruction consumes a parameter on the stack top, on the top of the stack, which is the caller, right? And this instruction checks the code size of an external address and push the result to the stack. So this action corresponds to the only human modifier in the source code. It requires the code size to be 0, and this is to be ensured that it's not calling from a contract address, but actually this check can be bypassed, and it's not very difficult to realize. It's not very difficult to implement, but we won't talk about it in this talk. So anyway, we know the result must be 0, so we just left the 0 here. And the next instruction is sLoad. It consumes 1 parameter and loads the value of that position and push the value back to the stack. So we just leave it here for now. Then load another value from 262A. So what is on this position? Let's back to the beginning of the contract creation code. Remember that we were replacing the runtime code by a piece of malicious code, right? Before return, there's a weird sStore, and it means stores a value to a position key in the permanent storage. So the position key here is this value 262A. Yeah, right. I might make a mistake in the very beginning, but just take what I said just now, okay? So this means that when it loads from this position, the value is always this 3C, CF, D6, and OB, okay? So to make it simple, we replace this loading action with the value, with this value. And wait, what is the meaning of this value? So by googling it, we can find that these 4 bytes happen to be the function signature of withdraw function. All right, we'll keep this in mind and move on. And next, two opcodes store the value to the memory 20, and the rest of the code basically pushes more values onto the stack. Now we are about to execute the jump instruction, and the position is jumping to is core data load 5E. And core data load means to copy specified 32 bytes from core data to the stack. So here we have another arbitrary jump by controlling the core data. Since we want to jump to the dedicated core gadget, right? Thus the core data load 5E should be 09A2, right? Now that we are about to execute dedicated core, let's compare the stack layout with the dedicated core parameters format. And they look very similar. So is very promising at this point. And let's check them one by one. So the first variable guess means the execution fee. And the second one, ADDR, it is the target address of delegate core, which should be the attacking contract address, so that we can execute more malicious code. And the third one, argument offset, is the starting position of the arguments when calling it. So it's the position on the memory, right? And this is a fixed value 3C. And if you check the memory, you will see that this happens to point to the start of the signature of withdraw function we got previously. And as for argument length, the value is storage 0, right? We leave it here before. So to figure out this value, we want to check the source code. So generally, in Solidity, global variables are stored in the storage in growing order, and the position is starting from 0. Thus, the storage at 0 corresponds to the version variable. So the value of it is 4. In other words, the argument data is starting from 3C and 4 bytes long, which is exactly the withdraw function signature, right? And last, the return offset and the return length together decide where to store the return value in the memory. So this is actually a carefully designed stack for the following delegate core to make it, and this is to make it calling a chosen address on the withdraw function. Okay, let's pause for a while and switch to the designer view for a little while. Okay, and there's a couple of interesting things. You might wonder that why do I use color ext code size and sload to represent push 0x4, right? And why do I use push 262A as load to represent push 0x 3CCF D6OB? Why not just use push 4 and simply just push the data to the stack? Because I want to hide the bytecode inside the sample answer string. But 04 and CFF6OB are not visible characters. Also, the storage position 262A was carefully chosen to avoid being overwritten during execution, and also to keep each byte in visible ASCII range. So all this effort is because I want to patch as little bytes as possible, trying to make the backdoor graceful and trying to make it clear for players to find the right way. Okay. All right. Now we know how to control the target contract to make delegate core and execute arbitrary code like transfer all the ether to us, right? But if we stop here and try delegate core with an attack contract like this, will it success? The answer is no. So let's see what's missing here. Don't worry, we're almost there. So during the delegate core, it consumes the top 6 slots on the stack and push back a success value to the stack and store the return value to memory. And then the success value is popped out and the program jumps to a stack value which was pushed earlier to the stack. So where did this value come from? Let's back to the earlier. The stack prepared by the second gadget has all been consumed by the delegate core, right? So the stack is so this piece of stack is balanced here. and it's also balanced for this piece of code. Thus, it is the top two it is the top two instructions that push the values on the stack and left until the end of delegate call. So we are clear about the stack layout at this moment. So we're gonna follow the jump. We jump to 0x049D, and we land on another gadget. It loads memory 402E and adds a value, then jump to the result. Since the result is an invalid address by default, so the EVM will throw an error and revert the whole transaction execution. And that's why we failed just now. Since we already executed the malicious code, so, now we need to make it jump to somewhere to stop the whole execution gracefully, right? So we need to figure out this value, what this value come from. Again, we need to back to earlier. We'll notice that before the first arbitrary jump, there is a push 0x04b1 instruction. And it turns out to be the value that we are looking for. So it will jump to our delegate core return value plus 04b1. And next, by searching through the whole bytecode, we're happy to see that there's a jump test followed by a stop, which is perfect to be the last gadget, to be our last gadget. And in order to jump to this landing point, we need the return value to be 152 minus 04b1, which is FFFFB7. And although there's an integral overflow, it's not important anymore, right? So finally, we got here. Here are all the traps and requirements we've encountered and gathered up. So some of them I didn't have time to explain the details, but they are not difficult to figure out, I think. So the only thing left for us is to assemble all these requirements, and the final payload look like this. The attacking contract transfers all the ether to the attacker and return a specific value. And the data variable is the payload calling to the from the attacker calling to the target contract. And here's the last design consideration. Remember that our true answer for the question is a single R, right? It's quite short. But if the player uses the fake answer, is longer and will interfere the value of call data 5e, which is one of our jump value, right? So this is designed as a hint to warn players that they are getting the wrong answer, and the correct one should be much shorter. But unexpectedly, it turns out to be a kind of distraction that's misleading players trying to shorten the answer, which would waste plenty of time. But anyway, we solved the challenge together, and it's time to wipe it up. So to solve this challenge, players need to find gadgets heading in strain, normal Opcode and swarm hash, right? And they need to control 4 gadget jumps by sender address, core data, and the return value. And there are 5 honeypot techniques used in it: hidden core by internal transaction, function signature collision, caller address reference, runtime code replacement, and the last one is jump-oriented programming, JOP, right? Okay. Special thanks to Peter 50216 from Team 217, who was the only one solved this challenge during the match. And special thanks to Level of Floor, who made some great videos to analyze this challenge. All right, that's it for today. The challenge name is Opcode Monica. I hope you enjoy it. And welcome to Real World CTF 2020. Have fun. Bye.